First, let's understand what statistically significant means. In statistics, significant does not mean very important like we use in daily life. It means that the result we see is probably not happening by chance. When a researcher says a result is statistically significant, it means the difference or pattern they found is likely real and not just random luck. Now, what is the level of significance? It is a small number that shows how much risk the researcher is willing to take of making a wrong decision. This wrong decision happens when we say something is true or different, but it actually is not. In statistics, this mistake is called a type 1 error. A type 1 error happens when we reject the null hypothesis even though it is actually true. The level of significance is written with the Greek letter alpha. Usually, researchers choose alpha equals 0.05, which means 5%. This means they are willing to accept a 5% chance of being wrong. If they choose alpha equals 0.01, they are being stricter, they only want a 1% chance of being wrong. If they choose alpha equals 0.10, they are being more relaxed, they can accept a 10% risk. The smaller the alpha, the stronger the proof needed to say the result is real. Now let's connect this idea to the p-value. When we run a statistical test, like a t-test or z-test, the computer or software gives us a p-value. I will show you example of this later in video. The p-value tells us how likely it is to get our result if there is actually no real effect. Once we have this p-value, we compare it with our chosen alpha level. As I told earlier, alpha is level of significance. We can set alpha equals 0.05, which means 5% chance of being wrong. Here's how it works in simple words. If the p-value is smaller than the alpha value, it means the result is statistically significant. We say the result is probably real, and we reject the null hypothesis. If the p-value is equal to or greater than the alpha value, it means the result is not significant. We don't have enough proof, and we keep the null hypothesis. Let's look at an example. Suppose researchers are testing a new medicine to see if it lowers blood pressure. The null hypothesis says the new medicine does not make any difference. After doing the experiment and using Excel to run the test, they find that the p-value equals 0.03. The chosen level of significance is alpha equals 0.05. Because 0.03 is smaller than 0.05, the researchers reject the null hypothesis. This means the medicine likely works because the chance of getting such a result by accident is only 3%, which is quite small. When we say a result is significant at the 5% level, it simply means the p-value is less than 0.05. When we say significant at the 1% level, it means the p-value is less than 0.01. These levels just show how careful the researcher is about making a mistake. Smaller levels, like 1%, show stronger confidence in the result. In Excel or other software, we don't really calculate the level of significance, we choose it before we start the test. Excel helps us find the p-value using the data, and then we compare it to alpha. For example, if your Excel output shows a p-value of 0.02 and your alpha is 0.05, you can tell your audience that the result is statistically significant because 0.02 is smaller than 0.05. Here, I've created a small dataset comparing two groups, one group that took a new drug, and another that took a placebo. The new drug group has higher numbers on average. So we'll test if this difference is statistically significant or if it might just be due to chance. To check this, I'm going to use a t-test, sample assuming equal variances from Excel's data analysis tool. I'll select my data ranges, variable 1, for the new drug, variable 2, for the placebo. For the hypothesized mean difference, I'll enter 0. This means I'm assuming that there is no real difference between the two groups. That's our null hypothesis. If our results show strong evidence against that, we'll reject it. Next, I'll set alpha equals 0.05. This number represents our level of significance, or how much risk we're willing to take of being wrong. In simple words, it means we accept a 5% chance of saying the drug works when actually, it doesn't, after running the test. Excel gives me these results: mean for new drug, 9.7, mean for placebo, 4.9, t-stat, 6.79, p2tail, 0.00000023, Critical two-tail. 2.10. Now, here's the most important part, interpreting the p-value compared to alpha. Our p-value equals 0.00000023, which is much smaller than 0.05. Since p is less than alpha, we reject the null hypothesis. This means the result is statistically significant. The difference between the new drug and placebo is very unlikely to be due to random chance. So, what does this tell us about the level of significance? It tells us how strict our test is. Because our p-value is far below 0.05, the evidence is very strong that the new drug truly works better than the placebo. If the p-value had been greater than 0.05, we would say the result is not significant, meaning we don't have enough proof to say the drug makes a real difference. Here's an easy way to remember the strength of the evidence. If the p-value is greater than 0.10, there is almost no evidence that anything is different. If the p-value is between 0.05 and 0.10, there is weak evidence. If the p-value is between 0.01 and 0.05, there is strong evidence. If the p-value is 0.01 or smaller, there is very strong evidence that the result is real. In short, the level of significance helps us decide when to trust our results. It sets the rule before the experiment begins. For example, if we say our alpha is 0.05, we are saying, I will only believe the result if the chance of it happening randomly is less than 5%. This helps researchers make fair and consistent decisions instead of guessing.